Hi all, and welcome back to the Crazy Small CPU video series, and this is going to be the last one where we make some wiring changes. So in the last video we actually had the A and B register produce output, and in fact we'd write up all of the control lines and we could single step and see A and B calculating values and storing them back into the RAM. So in this video we've now actually wired up the UART, the chip that will produce serial output, which we can send out to a display on another computer. Now, for the UART to work, we need 8 bits of ASCII data. And I've decided that the best place to get that is from the A and B registers, because we've got 4 bits on the A register, 4 bits on the B register. They've already got data loaded up. So if we can somehow, once they're loaded up, to trigger the UART to send that out to a serial port, that would be perfect, and we'd be able to see the characters. Now the control line for the UART is active low. Fortunately, the A load, where's the A load line, and the B load lines are both active low. So when they both go active low, if we could get the right line to go active low, then once we've loaded these two, then that would be the signal to send the data out across the data bus and into the UART and to be sent onto a remote screen display. Of course, the consequence of that is that once we assert A load and B load, then whatever is in the contents of the registers is going to be trashed, and they'll load whatever comes in from the multiplexer. But that's the price we pay when we don't have a lot of control lines and they're already busy doing some other tasks. So in my first design, I simply put in an OR gate so that A load and B load comes in. If any of those are 1, then the output will be 1, and of course we won't write. And only when both of them are zeros will we get a 0 on the control line, and that will go out to the UART. But when we tried that out, we found out that there were some glitches, and Chris Baird sent in a solution which was to include the clock signal as part of the controlling. So what happens is we assert A load and B load low, and the clock line also has to go low as well. Now, we need this because when the clock line is high, then that's the time when the registers actually do their loading. So what was happening before we were including the clock was that these two would go low, the UART would start doing some output, and then when the clock would go high, the contents of the registers would change and the UART would send out spurious characters. So now we have an OR gate followed by another OR gate, which effectively makes a 3-input OR gate. When all of them are low, that's the only time that the output on pin 6 of the 74LS32 can be low. We bring that down and plug that into the right line, active low, on the UM245 UART, and that's going to actually produce the right signaling to get it to write without any problems. So I've wired up the new version of the Crazy Small CPU, and I will update the schematic and I'll fix that up on the new version. So let's just have a look at an example program which we're going to use to test the output of the UART. So we're going to try and print out all of the printable ASCII characters, and the printable ASCII characters start down here at hexadecimal 20 and go all the way up to hexadecimal 7F. And remember with that, it's a 4-bit computer, so we can go from 20 to 21 and 21 to 22. But when we get to F, we are going to have to move that up to 0, but then also move the 2 up to a 3. So let's have a look at how we're going to do that. We've got 2 memory locations, low and high, and they're going to store the high nibble and the low nibble, the high 4 bits and the low 4 bits. So the first thing we need to do is initialize them to 20. So we can 0 the low one, and we can load 2 into the A register and store it into the high register, up the high location. So we start with 2, 0. So the next thing is to load them into A and B. So high goes into A, low goes into B, and we run the dab instruction. And the dab instruction will bring both A load and B load low, and therefore it'll print that out as a character on the UART. So we'll get a space printed out. Okay, the next task is to move up to the next 8-bit number. So we'll load low into the A register and run the instruction that increments the A register and stores it back into memory. So 0 becomes 1. Now, of course, if 0 becomes 1 It didn't overflow, but it didn't produce a carry because we didn't roll back down to 0. So therefore carry is clear. We can simply go back to the loop. We now have 21 in A and B, load those two and dab it out and print it on the UART. We fall back down and we keep incrementing 21, 22, 23, 24, 25, but eventually we'll get to 2F. We'll have outputted 2F, and then F will be incremented and it won't fit, but it will roll down and become a 0. And at this point in time, we'll have got a carry. So now that we've got a carry, we know that's gone back to 0. We now need to load the high nibble, increment the high nibble, store it back into the high nibble, and now we have 30 in A and B. Now we are going to loop back again, and this time we're going to loop back because once we get to 7F, that's still treated as a number which is positive. Remember, negative numbers are the numbers where the left-hand most significant bit is high, and 7F is 0, 1, 1, 1, 1. So we can loop back as long as the negative bit is clear. So eventually when we get to OX80, and that's the number 1000, that top bit is negative and we will fall out of the loop. So the last thing we're going to do is to load 0 into the A register, 10 into the B register. So that effectively gives us decimal 10 or ASCII 0A, or when we print that out as ASCII, that's the new line character. So print that out and go into an infinite loop so that the program counter will simply jump back to itself, and therefore we won't go into rubbish contents in our ROMs. Excellent. Well, I've actually got the CPU ready to go, and instead of getting its power from a USB device, I now can get the power out of the UM245R itself. So I'll just quickly go and plug it in, turn it on, and I'll come back and I'll have the laptop so we can see the display as well. Okay, I've got my laptop sitting on the desk on the right, and I've got the CPU ready to rock and roll on the left, and I've got that program loaded up into memory, into ROM. So what I'll quickly do, I'm single stepping, and of course it randomly starts at a strange location when you first turn it on. So I'm just going to reset the program counter. All right. Now what we're looking for is the fact that we've got the A load and B load LEDs lit up. We want them both to go to 0, and we also want the clock to go to 0. Then we'll have a look at and see what's on the A register and B register and see what gets printed out on the screen. Okay, so if I just single step through this pretty quickly. All right, now you can see that the high nibble is 0, and remember these are backwards, and the low nibble is 0 and the top nibble is 2, and we just printed out ASCII 20, which is space character. So let's single step a bit more. Okay, this time we've got 2 and 1, and the clock signal is 0, A load is 0, B load is 0, and so therefore we've just printed out ASCII 21, which is exclamation mark. So it looks like it's working. That's always a good sign. Next one, 22, and we get the double quote coming up. And the next one is 23, and we get the hash character coming out. So we're incrementing, we're moving up to the next one, $sign. Okay, and %sign. Oh, by the way, when we do the dab instruction, because we didn't say what address or what constant we're using, when you put that in the assembler, it will use 255 as, or all ones as the 8-bit value if you don't specify. And of course, that generally means that that's a location in memory that we're probably going to overwrite if we don't specify a particular address. And it also means that when we do the dab instruction, that is going to be loaded into the A and B registers. So as soon as I actually click on the clock pulse, then those all 1 bits get loaded into the A register. Now there is, so that means that you will lose your A and B registers when you do a dab instruction, but there's some optimizations as an assembly language programmer you can do that can optimize what you're doing there. Okay, so if I keep single stepping, you can see that this thing is working fine. All right, now I'm not going to go all the way up to all of the 96 printable characters. But what I might do is actually take the clock line over and put it onto the free running clock side of things, and we'll run it while it's over there. Okay, so I've just quickly moved a few things around and edited the video. What I've just done is I've taken the timer line, the clock line, from the single step side of things, and I've brought it over to the running clock side of things. I don't know, that's running at about, I don't know, 20 hertz or something like that. So when I let go of the master reset line, we'll actually run the program without me having to single step it. And of course, remember that when we get to the end of the printout, it'll go into an infinite loop. So let's try it out. Off it goes. And of course, it looks really pretty. It's coming up to Christmas, so maybe I should stick my CPU on the Christmas tree because it'll be fun. And it's a hell of a lot faster than me having to press that button. Okay, we're up to the uppercase. We might even run off the end of the screen. I might even have to move it over. Yeah, here we go. And, oh, you can't see, I haven't got line wrap on, so, and it finished. Yes, all done. And if I bring the CPU back into shot, you'll see that even though the clock light is still going, that we're stuck at the same program counter value, and so we've hit the infinite loop. There you go. So we now have a fully working computer with ASCII output out to a screen. And of course we can now run it in a stable mode, so free running clock, and we don't have to single step it anymore. So maybe in a future video I'll actually go through the whole assembly, or maybe compile, assemble, insert into ROM and run process.